These are the notes for Unit 2, Day 2. And you should have your textbook ready for the notes that you're going to be taking just a few minutes. But also, you need to bring your textbook to class for, I'll remind you again, but for when we do the classwork for Day 3. But I'll remind you again in the next note session for Day 3. Okay, so today's notes start on page 7 of your packet, and we're talking about differentiability. So differentiability is kind of a the ability to, we have the word ability here, the ability to differentiate a function. So we talked about the derivative, and we know that the derivative and the limit method are the same thing. So what we're trying to do now in this note session is we want to figure out when a function is differentiable and when that process fails. So when does the derivative fail to exist? So it's kind of either or. Either this function is differentiable or the function fails to be differentiable. So that's kind of what we're looking at. Okay, so in order to kind of get your mindset, to give you a visual with the word derivative, I kind of start this saying. So when I say derivative, you think slope, right? We know that the derivative is the slope of the tangent line. So, and we have to start equating those two things. We know slope is basically an algebra process, right? Rise over run. I mean, that's what we kind of think of. But we know that when we're talking about the derivative, we're talking about tangent line. So when I say derivative, you have to think of slope of the tangent line, or just slope at that point, right? Because that's what a tangent line is. So now I'm going to reverse that. When I say slope, I need you to start thinking derivative. Okay, so I'm gonna say this a lot to you over the course of the course. Okay, so central question: when is the function differentiable? When does the derivative fail to exist? So like I said, these two are kind of either or situations. So as we address one, we can kind of address the other. Okay, so this is where you need your textbook. Remember, there is an E version of your textbook in the left sidebar in Blackboard as well. So we're going into the textbook. I just want you to pause the video for no more than 3 minutes. I really want you to crank this out. Derivatives fail to exist at the following locations. So we are looking for the failure of a derivative to exist. I call these problem spots, right? We can't take the derivative because these are these locations. Okay, so turn to page 105 and 106 in your book. Identify and diagram the 4 ways. There's 4 ways, right? That's why I got 4 things here in which the derivative fails to exist. So 4 problem spots, basically, is what I'm talking about. Okay, pause the video. You've got 3 minutes. If you've started the video again, I'm assuming you've taken the notes. I'm just going to say this: if you haven't taken the notes, seriously pause it and go through the process of taking the notes. Okay, it's called a kinesthetic process. You're doing something, and it really helps you remember it better. So I'll give you one more time, one more chance. Stop the video and take the notes. Okay, hopefully I've appealed to your sense of wanting to remember this, and you've already taken the notes. And so I'm going to go through these 4 situations in which the derivative fails to exist. Okay, so the one situation where the derivative fails to exist is a corner. Okay, so absolute value functions are a perfect example of this because they have corners. They have pointy points, like I like to call them. So if you think about, when I say derivative, you think slope. Think about the slope, right? The slope here is negative and the slope here is positive. So if we're at this point right here, we don't know if we're on the negative line or the positive line. So we just say the derivative doesn't exist. It's confusing. We don't know which value to use. So when we have a pointy point, when we have a corner, technically, it's a location at which the derivative fails to exist. Now, caveat here, kind of a sidebar, if we were just to look at this line on the left, the one with the negative slope, we could find the derivative all along this line. Likewise, we could find the derivative all along this line with positive slope. We just can't do it right there at the point. All right, second one is a cusp. Cusps and corners are kind of the same thing. What distinguishes them is that cusps involve curves. So we have a cusp and we have a curve as part of the piecewise function. So f of x equals x to the 2/3 power is this thing that's got this curve, and then it has a point just like the corner does, and then it goes into a different curve. So a lot of same characteristics here. We cannot define the derivative right at this location where this cusp is. This doesn't always occur at the origin. Okay, we could slide this horizontally over. We just put like -2, the cusp would be over here at 2. So we could slide this cusp anywhere. We could slide it up or slide it down. Actually, if we put a -2 here, the cusp would be down here at -2. Sorry about that. I made a mistake there. So we could relocate that cusp. Same with the corner. Okay. Number 3 is a vertical tangent. So this function is f of x equals the cubed root of x. So that's x to the 1/3 power, if you think about powers and roots and how they're connected. And so when we have an x to the 1/3 power, we can take a negative root and we can take a positive root and find an answer. And so this one is curved, and then it comes into a vertical position here, and then it curves like a root would curve in the first quadrant. So at this location, and again, we can offset this. We can offset this left or right or up or down. It doesn't have to be at the origin. At this location, the function literally goes vertical. And we know that if I say derivative, you think slope. The tangent line being vertical right here, we know that that is infinite or undefined. So we say that the derivative fails at a vertical tangent because we have infinite slope. And so infinite and undefined are kind of synonymous. They're the same thing. Okay, and then any discontinuity. Anytime we have a jump or a hole, remember all those discontinuities, a jump or a hole or a vertical asymptote or an oscillation, okay? And oscillations are really rare, so I would put that kind of in the back of my memory. Any discontinuity, we do not have a defined derivative. So even though we are just defined right here, because we have this jump here, we say the derivative doesn't exist. And again, it doesn't have to be right on the y-axis. We could offset this in any direction as well. I just stuck to these pictures because those are the pictures in your textbook. Okay, so derivatives on our calculator. This is really kind of cool. We can do a derivative on a calculator. We'll actually find a numeric value. But there are some times at which it also kind of gets us in trouble. So we got to be a little smarter than our calculators. All right, so derivative on a calculator, compute the derivative of a function at a point. Okay, now I want to caution you here. I want you to get your graphing calculator out. And so if you need to use the graphing calculator on your iPad because for some reason you don't have it with you, that's okay. But you really, really, really need your handheld one, both in class and taking notes. This isn't in the notes, but yeah, I want you to actively participate here, right? I want you to really be engaged. Okay, so here we have a function. It's f of x equals x cubed, and I want you to calculate the derivative at x equals 0 and x equals 4. So I want you to calculate the derivative right here at this location, and 1, 2, 3, 4 at that location. Okay, now I say derivative, you think slope. So you can probably guess what the slope is at the origin. It would be harder to guess what the slope is up here to the tangent line. It looks pretty vertical. Okay, so calculating the derivative on your calculator is using the Math 8 key. So if you look at your calculator, I'm looking at my calculator right now. The Math key is on the left-hand side. It's the third button down. It's underneath your alpha key. And the 8 is just the 8th option underneath that menu. Okay, so I'm not sure if anybody has a TI-83 anymore. Those are pretty old. Most people have a TI-84, but these are the two notations that you could possibly see. Now, before we dive into this, if you've got an 83, this n deriv means this notation, right? We were familiar with this notation. This is the ddx notation. And so if you have an 83, the syntax, the programming is a little bit different. It's a little more rooted, it's like an earlier version or earlier generation. Let me know though if you're getting confused with this notation, because I can help you through that. If you have an 83, you got to live with this notation. If you have an 84, you should see this notation. If you see this notation on an 84, let me know. I can update your operating system so you see the math type notation that looks more like what you write. Okay, so this is how we use Math 8. So here's our screen. And when you select Math 8, this will come up or this will come up. I'm kind of doing both screens at the same time. Okay, so let's do the TI-84 first. So what you want to do is you want to use your variable key. Remember, your variable key is just underneath your mode key. So it's the second one down, second one over. We want to put a variable X here. And this X, if it's not already there, we want to put a variable X there. Okay, so in this box is where the function goes. So we're going to put X cubed there. And in this box is a numeric value. So in this case, we're going to put 0 first. Okay, and then we're going to hit enter. In the old notation, you would have to do this, X cubed. So the function comes first, and then we have a comma, and then we have an X. That's this X here. That's the variable of integration. We call it a dummy variable. It's just telling us the variable of differentiation, excuse me. It's telling us what we're using on our x-axis. And then 0 is that numeric location. Okay, when we press enter, we get this. Now this might be a little bit of a surprise to you, 1e minus 6. So this is scientific notation. So 1 times 10 to the minus 6 is 0.000001. Okay, now your calculator is finding the derivative numerically. So it's approximating. Remember, we talked about approximating the derivative, right? We can approximate the derivative by doing the algebra slope, and that's exactly what your calculator is doing. So it's taking smaller and smaller bytes and trying to find the slope, and it's coming really close to 0, but it should be exactly 0. Okay, so we have to, let me back that up. We have to, when we see 1 times 10 to the minus 6, we have to think 0. Okay, it's the approximation capabilities of our calculator. Okay, so that shouldn't be any surprise, right? And when x equals 0, our tangent line is horizontal. We know the slope, right? I say derivative, you think slope. We know that the slope of a horizontal line is 0. Okay, let's go to when x equals 4. So we're going to do the same thing. We're going to put our dummy variable in, and we're going to put our function in, and we're going to put 4 here. So that means in the old notation, we're going to put our function, x cubed, we're going to put our dummy variable, x, and we're going to put our numeric value here, 4. And then we're going to hit enter. And so now we get 48. Notice on the older calculators, again, that approximation that the calculator is doing is giving you a lot of, look at this, this is the 1e to the minus 6, right? So we can essentially ignore that and just call that 48. So when x equals 4, that point of tangency up there, it's almost off the screen. If we draw a tangent line through that point, that slope is going to be 48. So I say derivative, we're looking at slope, right? That's what we're thinking here. Okay, so let's take a look at then how to find the derivative using a graphing function. So in this video here, I'm setting up my window, and I'm adjusting my window because I want to graph x cubed, right? So I need to, and I want to talk about that location at x equals 4. So I need to go up to 48. So I went way up and down to 70, right? So we can get this on the window. And now I'm going to put the function in. So this is another way to find the derivative. This is kind of cool. So there's my x cubed, right? And I'm going to hit graph. And so here's my function, right? That's kind of what the other screen looked like, all right? And I'm going to go out to 4 here, and I'm going to graph that tangent line. So this is kind of cool. I'm going to use that calc feature. Second, calc, and notice there's a dy dx. So I'm going to arrow down and select that, and it's going to give me a whole bunch of information on my graph screen. Okay, so right now I'm at 0. I want to type in 4. right? Because that's the point I want. And then I can hit enter, and it's going to give me a ton of information at the bottom of the screen. So I have all this information down here, but look at this. I have the derivative right there, and I have the x and the y coordinates, right? 4 cubed is 64. So that's another way to also calculate the derivative if you want to graph it. So just, another option, you can either do it from your calculator screen or you can do it from the graph screen. Okay, so this is when the calculator idea kind of blows up. Because the calculator is approximating the slope of the tangent line, it's taking points on either side of that point and kind of getting closer and closer and closer to the location. Well, if we did that on an absolute value function, we would keep going across on either side. You can see that that might be problematic. Okay, by inspection, we know that the derivative doesn't exist because it's a corner, right? And that's when the derivative fails to exist. But what does your calculator think? So we can put in the absolute value function. Absolute value is under the math key. And if you arrow to the right under NUM, it stands for number, you'll see it's the first option. So I put the absolute value in. That's what ABS is here with the 83 notation. And when you hit enter, it gives you a slope of 0. Now, ironically, it doesn't give you a slope of 1 times 10 to the minus 6. And this does this because of the numeric approximation, right? If we pick a point here and then we pick a point straight over on the other side and take those 2 points and calculate our slope to try to approximate it, we're going to get a 0, right? We're going to get a slope of 0, and that's not really what's happening down here. But that's what your calculator thinks. So this is where your calculator fails. And so we have to be really super careful that, and that's why it's important to know the shapes of functions. And I have an anchor chart in the classroom above our AP, right next to the limit flowchart that has the shape of about 20 functions. I'm looking at it right now. Know the shapes of those functions. So that you can find those points of non-differentiability visually, because your calculator won't always calculate that correctly. Okay, so the definition of differentiable: we can't have pointy points. We can't have vertical behaviors, and we can't have any discontinuity. Right? So a function, here's the definition, it's in your notes. A function is differentiable if it has a derivative everywhere in its domain. Okay, so it must be continuous and smooth. So no pointy points, no gaps, no discontinuities, right? No vertical locations of the function. Functions at closed intervals must have one-sided derivatives defined at the endpoints. So we'll talk about what that means. So continuous, no holes, no jumps, no asymptotes, no oscillations. Oscillations are rare. Okay. In other words, if it's continuous, you don't have to lift your pencil in order to draw it. Remember that? And that's the kind of the everyday, using the everyday verbiage. So no discontinuities. It's got to be smooth. So no points of non-differentiability. Okay, so continuous and differentiable. That's really how we should look at this. No cusps, corners, vertical asymptotes, or discontinuities. Okay, so 2 theorems that are kind of obscure. Differentiability implies continuity. Okay, in other words, if I can calculate the derivative, then that function is continuous at that point. Okay. So what is that implying? Derivative implies that the limit exists, it's continuous, and it's smooth, right? The derivative has to be continuous and smooth. So by definition, then, if it has to be continuous, then it is continuous. Since a function must be continuous to have a derivative, if it has a derivative, then it's continuous. So that's kind of what we're thinking there. So that's why we say differentiability. If I can find the derivative, then I know I have a continuous function at that point. Theorem 2, intermediate value theorem for derivatives. So we had an intermediate value theorem already. We were talking about it in terms of just regular function value. But we have an intermediate value theorem for derivatives as well. It goes kind of like this, right? Intermediate means between. So if A and B are points on the interval and of the function f, and function f is differentiable, okay, then the derivative takes on every value. Okay, so kind of like the function takes on every value, so does the derivative on continuous functions. Okay, and we know this function is continuous, even though it doesn't say it, right? I don't see the word continuous anywhere in this theorem, but it's differentiable. And we know that differentiability implies continuity. So even though you don't see the word continuous here, because you see the word differentiable, we know it's continuous because of the previous theorem. So let's take a look at this function here. So this is really what it means. Let's take a look at this location, call it location A. We know the slope of the tangent line, or the derivative, is a half. Let's take a look at location B here. We know that the derivative, or the slope of the tangent line here, is 3. So the question is, what is the slope of the tangent line at this location C? And here are our options. Is it 0? Is it negative a half? I'm not quite sure why this is blue. Is it 1? Or is it 4? And according to this theorem, it's got to be between a half and 3. So which option is between a half and 3? Oops. That I guess it didn't circle it. So which option is between a half and 3? Option C. So that this has to be 1. It can't be 0. It can't be negative a half, and it can't be 4. So the answer here is C. I'm not quite sure why it didn't get circled. Okay, so using that, let's just kind of check our understanding here. So we have a graphical identification, and we're checking for differentiability, right? So function G is graphed below. It looks like a nasty little piecewise function. The dashed lines represent asymptotes. So we talked about this. This vertical asymptote is at -1. This asymptote here is at -3, but it doesn't apply here, right? It crosses this function here, and that's okay, because this asymptote really applies to the right end behavior. So we don't really care about the fact that it goes all the way across the screen. So select all the values for which G is not differentiable. So where does our differentiability fail? Well, it fails when we're not continuous, right? So it fails here, and it fails here at this jump, and it fails here at this asymptote. So does it fail at -8? Yes, it does. So we're going to circle that. Oh, they're all at the same time. Rats. Spoiler alert. Does it fail at -2? Yes, it does. Does it fail at 1? Yes, it does. Does it fail at 3? Nope. It's smooth and continuous right through 3, so we can calculate a derivative. Oh, I'm sorry. -3. Rats. That's a -3 over here. My bad. But same argument, right? -3 right here. The function is smooth and continuous, so we can calculate the derivative at -3. So the derivative fails, right? Does not exist at A and C and D. All right, let's take a look at function H. The dashed lines represents asymptotes. I don't see any dashed lines. Select all values for which H is not differentiable. So we're looking for those points of non-differentiability, right? Cusps, corners, vertical asymptotes, and any discontinuity. So -3. Where's -3? Here's -3. I got it right this first time. Smooth and continuous. We're good there. -1. Here's -1. That's a cusp, right? We've got a curve coming into another curve. That's a cusp. So that's not differentiable. So B, it fails to exist. C, 1. 1 is right here. That looks like a vertical tangent to me, right? So that derivative fails to exist there. And 4, D, this looks continuous and smooth, so we're good there. So B and C, we have our cusp at B and our vertical asymptote at C. Those are our points of non-differentiability. So the derivative does not exist. It fails there. Okay, let's take a look at this. This is a little more complicated. It says, is the function below continuous and or differentiable at x equals 3? So notice it's piecewise. They love to ask these kind of questions. It's piecewise. We have a problem at 3. We have to check. We have to check for continuity, and we have to check for differentiability. Okay? And that requires 2 checks. continuity is a function check, right? We're going to stick 3 in here and 3 in here and see what we get. Differentiability is a derivative check. So we're going to need our calculator to do that. Okay, so continuity, functions are equal. Let's check to see if that's in fact the case. Differentiability, derivatives are equal. That's where we need our calculator, our math 8. Okay, so let's check continuity. I stick 3 into x squared, I get 9. I stick 3 into 6x minus 9, and I get 18 minus 9 is 9. So I get the same value. So we know we have a continuous function. So it's either A or it's C, right? Because those are the continuous ones. Okay, let's check the derivative. So I take x squared and I stick it into my calculator and I do a math 8. And or if I wanted to, I could graph it and do it that way. And when I do that and evaluate it at 3, I get 6. And when I stick 6x minus 9 into my calculator and do a math 8, I also get 6. So I get the same derivatives, so it's differentiable. So it's both continuous and differentiable, so it's both of them. So it's option C. Let's take a look at this next example. Same thing. Notice again, is it continuous and differentiable at x equals -2? It's piecewise. They're always going to ask you about the problem spot, right, where it switches from one function to the next. So we're going to go through the same routine. Let's check continuity. Let's stick in -2 here. Remember, when you square a negative, it's positive. So -2 squared is 4 times a -1.5 is -6. And now I'm going to put a -2 here. -2, 6 times -2 minus 5 is -17. It's not continuous. Okay. And if it's not continuous, guess what? It can't be differentiable, right? If it's not continuous, that means there either is a hole or a jump or an asymptote, right? We can't have differentiability there. So if it's not continuous, we don't even have to do the calculator part of this question. We know if it's not continuous, it's not differentiable. So that's kind of a way of shortcutting your answer. You're not going to get even if you get the same derivative here, you can't call it differentiable because it's not continuous. Okay, so our chapter 2 definition, or not chapter 2, excuse me, our unit 1 definition, right? This is the limit method. This is a typo. This is the limit method, right? We call that the slope of the curve at the point. We know it's the derivative, right? So our new definition, gosh darn it, these are pretty bad. Bear with me here. That's really bothering me. This is our unit 1 definition. And this is our unit 2 definition. We've had a little bit of a redesign. Okay, play from current slide. Sorry about that. There we go, much better. So this is our limit method. Our current definition is the derivative of a function, right? We're no longer, we know that when we say slope, we mean derivative, and we're talking about a tangent line. And we know we're talking about the tangent line because we've taken the limit method here. So now what we're doing is, it's subtle, right? What we're saying is we're not going to use the M designation anymore. That's algebra. We're going to use the derivative notation. Okay, we're not going to call it A anymore, because what we want to be able to do is find the derivative anywhere, and our calculator does that for us. So now we can, instead of calling it A and being limited, no pun intended, but kind of funny, limited to one point, we're going to call this X so that we can find the derivative at any point. That's what our calculator does, right? So so now this is our updated version of that definition. Okay, we once said slope, we're now saying derivative. Okay, now this is the interesting thing. We have 2 ways of writing this. We can use that offset, right? F of x plus h. In other words, we're at x and then we move over h. Or sometimes College Board uses this notation where we just have these 2 points, any point and a location. And it doesn't change anything. It's just a different way of writing the derivative. Okay, so kind of get comfortable with these 2 notations. I'm going to use them interchangeably, and so does the College Board. Okay, so let's apply the definitions derivative. So look at these. These are all, right? This is all looking like the previous screen. It's all kind of looking like this stuff, right? So it says, which of the following is equal to the derivative of function g at 2? So I want to evaluate the derivative at 2 of the log of x. Okay, well, so we know that the a value is 2, right? If we go back to here, you know the a value, right, back to unit 1 is 2. So let's see what we have here. We know this is a non-starter, right? Because the plus sign is over here in the beginning, right? Okay, so so if a is 2, we have it right here, right? 2 plus h and then minus log 2 over h. Okay, so that's the definition of the derivative at 2. Right, all of these have kind of like D has an X where they should have a 2. C has an X over here where it should have a 2. This is just backwards, right? And it has no 2. Okay, so which now here we're kind of going in the other direction. Which derivative is described by the following expression? So we have cosine of x minus 1 over x minus 0. So think about 1. 1 is the cosine of 0. Does that make sense? Okay, so really you have to read this as cosine of x minus cosine of 0 over x minus 0. So I'm gonna back this up again. It's this form. Okay. Cosine of x minus cosine of 0 over x minus 0. Okay. So that's got to be the derivative of g of x when x is equal to 0. So we're evaluating the derivative of this function, cosine, right? I'm going to back up again, because when we look at these are the functions, right? F of x. You can find it over in this notation over here. You can find the function in this notation in the first location. So there's your function. It's cosine. So you know it's cosine, and we're evaluating it at location 0, right? It's our a location. So it's got to be this this expression for the derivative. Okay, when we get back into class, we'll work on those two concepts with our topic questions.